Hello everyone. Today I will be concentrating on the lecture which is particularly on the extensive survey project, which is for the sixth semester civil engineering students. This lecture will concentrate on only the new tank project. I will not go much into the detail of the survey work that you have carried on this site, particularly for the bund or for the canals or you have done some capacity contouring and all. So here, after doing the survey that is on the site which you have selected, which is suitable for the bund, you might have taken L sections and cross sections for a bund. You might have taken L sections for a canal after fixing the alignment of the canal. Then you might have done the capacity contouring, particularly to decide the reservoir capacity. You might have done the reconnaissance survey for the bund, where you can locate the catchment area, and for which you have to collect the topo sheet, because you can't do the survey for the entire catchment area. There is a wrong feeling that when we do capacity contours, so from the capacity contours that is generated, we can calculate the catchment area. Actually, it is not so. So many of the students do use the same capacity contours for the catchment area. So you should know that the catchment area or the reservoir and the reservoir area are totally two different quantities. So catchment area should be got from the topo sheet, and the reservoir area can always be calculated from the capacity contours that you have generated after doing a total station survey for the reservoir area. Dr. R.SHREEDHAR, Professor and Head, Department of Civil Engineering at KLS Gokul Institute of Technology, Belgavi. I do welcome to this lecture, which is particularly on a new tank project. So what is the first step that you do? So after you do the survey, so now you have to collect the rainfall data. At least 30 years of rainfall data have to be collected for the site from any nearby rain gauge stations. So in this case, we have selected 30 years of data, that is from 1987 to 2018. You can also collect 2019 data also. For you have seen that for 1987, so the annual rainfall is 1160 millimeters, and goes on varying. And in 2018, so it was somewhere around 2010 millimeters. So after the rainfall data is collected, and what you have to do is that you have to enter all the readings against that particular year in an Excel sheet. So it will be very easy for you to enter the rainfall data in the Excel sheet, so that you can sort it out in the descending order. So now you can observe that the highest rainfall is in the year 2017, which is 2226, whereas the lowest rainfall is in the year 2002, which is in the serial number 32, which is 681.1. So my very idea is to find out what is known as a dependable rainfall. So because you cannot design the bund for the highest rainfall, which is 2226 millimeters, whereas you cannot design the bund for the lowest rainfall. So somewhere a via media between this highest and the lowest rainfall has to be taken. So for that, we know that what is known as a dependable rainfall. So dependability is generally taken around 60 to 75%. So taking on the lower side, so we take dependable rainfall as 60%. So 60% of the total the number of years of data collected. So that means number of years of data collected is 32. So 60% of 32 comes to to around 19. So serial number 19, which is that is 1050. So that means you have to design the bund for this particular rainfall. That means this dependable rainfall is means what 1050 rainfall. That is it is coming for 60% of the year. So for 19 years. So for out of 32 years. So that is what it means. So it is because this rainfall is useful, because of this rainfall, so we can calculate what is the runoff in the catchment by using strange curves. So once we know the runoff, then we can knowing the catchment area, we can find out what is the runoff for volume. It is not that what survey you do on the site, to what level you do the survey. Suppose you do the survey to 128 level, and that's why you fix the bund to 128. It is not like that. It is the amount of rainfall occurring in that particular catchment and how much it is been converted into the runoff is to be decided, and then the storage volume has to be decided. So that's the reason why we go for what is known as a dependable rainfall, and then decide the storage volume. For that storage volume, we go for the design of the bund after fixing the normal reservoir level as well as the maximum water level. So now taking dependability as 60 to 75%, I have taken dependability as 60%. So number of years of rainfall collected is 32. So therefore we get the rank, that is 19. So 19th serial number gives 1050, as I told you in the previous slide. So therefore for my calculations, the dependable rainfall will be 1050 millimeters. So now for 1050 millimeters, that is 105 centimeters, taking the average catchment or a good catchment. You can take good catchment also. Taking good catchments here, so it comes here. Okay, so from here, from 105, taking a good catchment, so it comes to about 30 something like 39. So therefore I've taken the runoff as 39 centimeters. So for dependable rainfall, 1050 millimeters, and the runoff from the strange curves, we call this as the strange curves, which are available in the standard textbooks. So you can use this for 105 for a good catchment, you get about 39 centimeters of runoff. So now next step is to know the catchment area. It is not the capacity contours that you have generated and the areas that is enclosed between the curves is not the catchment area. The catchment area is totally different. So what you have to do is that we have to take a topo sheet, mark the ridge lines, and then get the catchment area from the planimeter and using this case. So for example, for this we have measured from the topo sheet and got as 2.145 kilometers square, so which comes to so much meter square. So therefore now, so use this data for the calculation, not the capacity contours, the area that you got from the capacity contours. So that is the thing that you have to follow to get the catchment area. So now to find out the storage volume between successive contours, you know that you have already generated the areas. Suppose you have the contours which are generated, and then we have one more contours which are generated at a particular level. So then you can find what is the area store, what is the volume that is stored between these two contours. For example, this is 100 contours, this is 101 contours. So you know the interval is 1 meter. So therefore H becomes 1 meter. Area A1 is this A1, and A2 is this area, A1 is this area. So that the volume that is generated between these two contours is got by this particular formula. So that is what is shown in the next calculation. So the next step is to for each of the contours that have been generated. Now you should find the areas generated by that particular contour. For example, A1 is the area of the contours that is generated by 117.5 RL. So similarly, A2 is the area that is being generated by the contour of RL 118. So knowing each of these areas like A1, A2 to A23. So we can find out the volume generated between two successive contours. So now the contour interval between two successive contour is 0.5. So therefore it is one third of this area, that is A1 plus A2 area plus root of A1 A2, close the bracket, multiply by h, that is 0.5. So we get the volume 4096. Like this we try to generate the volume between the contour A2 and A3, or A3 and A4, we write it here. So similarly A4 and F5 we write it here. So like this if the area is the volume generated between A22 and A23 is like 1,35,678 meter cube. So now the area volume generated between two successive contours have been calculated and entered in this table. Now from the previous calculation we know that the runoff volume is 39 centimeters, which comes to 0.39 meters, and we know the catchment area. This catchment area is not the area, is the sum total of this area. It is the area that has been got from the topo sheet. So you have to mark the ridge line on a topo sheet and then measure the area or determine the area using the planimeter. So this is the area that we got, which we have measured using planimeter, and that is particularly got from the topo sheet. So taking the catchment area and multiplying by the runoff depth, we give the runoff volume. Now the runoff, for this runoff volume you have to find out what is the RL. So that will be shown in the next step. So now that particular level which correspond to this volume, which is 8,36,550 meter cube, is the FRL. So if you give zero point 0.5 meters as the driving head for the surplus weir, you will get maximum water level. Then you give a freeboard to maximum water level, that will give the top of the bund. So that will be the top of the bund, and top of the bund minus the lowest RL will give the height of the bund. It is not the level to which you do the maximum level to which you do the survey and then fix up the bund height. It is the depth, the depth of water which comes as a runoff, and to what is the storage volume for that particular level has to be decided, and then you have to decide the top of the bund. The next table shows. So now for each of the successive contours we have found out the volume. So now go on adding up, you will get the cumulative volumes. So that means up to 127, this is the volume of the water stored. Up to 127.5, this is the volume of the water stored. Up to 128, this is the volume of the water stored in the reservoir. Now I told you that 806 comes somewhere nearer to this, so somewhere nearer to this cumulative volume, and that's the FRL for you. So therefore the FRL will be somewhere around 128 meters. So this is how you fix the FTL or a full tank level. Okay, so this is the steps that you have to follow to decide the normal tank level or the normal reservoir level, or also called the full tank level. So now we have found out the runoff volume from the previous volume. See from this table, where does it fit? So that RL is nothing but the FTL. Now, so now rest all the calculation starts. So we have fixed here 128 is the is fixed. Now 128 meters is the RL that is corresponding to this cubic meter. Now the full tank level becomes 128. Give a driving head of 0.5 meters for the surplus weir, so therefore that we get 128.5. Anything that the level that comes above 128 will go up to 128.5, particularly during the floods. So we have given a 0.5 meters as the driving head. Now keeping the freeboard of 1.5 meters above the maximum tank level, so we get the top of the bund. So now for the bund, the bund height gets fixed 130, and we know that the lowest RL is 117.5 at the side, so therefore 12.5 meters is the height of the bund. This is the height of the bund that you have to fix in the side. It is not the survey that you do on level the RL, the up to survey where you do and you construct the bund. So the bund height has to be decided decided upon the volume of the storage that you can have, which will depend upon the rainfall in that particular area. So now taking 10% as the gross storage, you can decide what is the gross storage. So therefore this is the live storage, which is 752,895 meter cube. So now for 83655 meter cube, again you see in the table it fits between the RL 122.5 and 123. And so the RL of the dead storage, we have to interpolate between these two values so that you get 122.7. So now the RL of the dead storage is somewhere around 122.7, and that fixes of the canal bed level for the calculations. So I'm not going into the detail of the design of the earthen bund and to do and to do the stability analysis. However, I have fixed the lowest. Okay, you know that lowest RL is 117.5. We have already fixed the full tank level, which is 128. We have kept the driving head, which is 0.5 meters. Hence, the maximum tank level comes to 128.5. I have given a freeboard of 1.5, so that fixes the top of the bund. So now you know that the height of the bund is 12.5 meters. So now the minimum, so here the minimum pool level is somewhere, because the lowest level comes to about 123.7 meters. So therefore the minimum pool level is taken around 123.7. The top width of the dam, as well as the downstream slope. So you have to fix the downstream slope, which is 2 horizontal to 1 vertical. So since we have assumed this slope, you can check the stability of the slope by Swedish circle method or slip circle method, and see that factor safety it will be safe. Similarly, you can provide the not a homogeneous dam. You can go for a hearting zone where top width can be kept as 1.5 meters and slope can be kept as 0.5 horizontal to 1 vertical. You can fix the material of the hearting zone as clay mixed with fine sand or fine gravel, and you can provide a rock toe also, which usually ranges from 150 to it consists of boulders of sizes usually ranging from 150 to 200 millimeters. So this is how you design the earthen bund. There are few formulas for fixing the preliminary sections of the earthen bund. You can refer those preliminary sections for the earthen bund, and then decide the top width. Also you can decide the freeboard, and then you can use slip circle method to decide the slope. You can do a number of trials for the earthen bund and see that you get the safe factor of safety, which will be more than 1.5. So okay, next step is to find we have fixed the canal bed level somewhere at the dead storage level, that is 122.7 meters. So we have reservoir live storage, which comes to about 752,895 meter cube. Here this is meter cube. Okay, so now we are assuming 10% losses goes for evaporation. Therefore, the volume of water that is available is 0.9 times 752,895 meter cube, which comes to about 67.76 hectare meters. Now you can decide about the crops. So I have taken one crop, so you can have 2 or 3 crops depending upon the command area. So therefore, one sample calculations has been given. So based on that, you can decide what should be the discharge in the canal. So for particularly for the wheat, so we have a base period of 120 days, where the duty is about 1800 hectares per cumex. So therefore you can decide the delta, which is 8.64 b by duty. So 8.64 into 120 days divided by duty, which is comes to about 0.576 meters. So therefore the depth of water that is required is 0.576 meters. Now we have two canals, which is left bank canal as well as right bank canal. So therefore we can decide what should be the area under irrigation. So the area under irrigation for both the canals, so that is we can say that it is so volume of the water is 67.76 hectometers, that is divided by the depth, so it gives so many hectares. So therefore for both the canal, so much hectares of areas will be irrigated, which comes to about 117 hectares. Now you can decide about the discharge in each of the canals. So that is the area divided by the duty, and hence divided by 2, because there are two canals. For one canal canal, the discharge can be 0.0327 meter cube per second. So you can for allowing for the losses, you can take 25% more. So therefore 1.25 into this gives 0.041 meter cube per second. So you can now use any of the methods. In this case, we have assumed the bed width of the canal, we have assumed the depth of the flow. So taking bed width as zero point 0.3 meters, depth of the flow as 0.5 meters, side slope of the canal 1.5 is to 1, that is 1.5 is to 1. So then you can calculate water area, which is y into b plus zy, which comes 0.525 meters square. Similarly, wetted perimeter is b plus 2y root of 1 plus z square, which comes to 2.1. Hence hydraulic mean radius can be calculated. Now you know that the bed slope can be fixed, which is 1 is to 1000. So therefore you Manning's n can be taken as 0.025. Hence velocity of flow in the canal can be calculated, which comes to about 0.5 meter per second. Hence discharge is area into velocity, which is 0.20, is well above 0.041 meter cube per second. But actually the required discharge is only 0.041, where the design discharge comes to about 0.2625 meter cube per second. So this is how you design the canals, where the left bank and in the left bank and the right bank canals. The next part is to the going for the tank sluice. Here we have two tank sluices, one for the left bank canal, another for the right bank canal. So we have to see that the water from the reservoir is sent to the canals. So in the case of tank sluice, the first step is to design the ventway. So now I have told you that the normal pool level is already decided, which is 128, meters. So canal bed level, you know that we have fixed it at 122.7, which is taken from the design sheets again, and minimum pool level is 123.7. So now generally even the normal supplies of flow can be given to the canals even the water level reaches the minimum pool level. So therefore it is 123.7 minus 121, which is 1 meters of water. But generally we don't design the sluice for 1 meter, so we design as a driving head somewhere around 0.25 meters, so that we get a larger opening, so that we can close the shutter as we want. So therefore discharge is given as CD A root 2 GH. So the discharge is 0.041, which you have taken. So zero point 0.6 is the CD. A is the area of the vent. So therefore we can H is the driving head, which we have taken for the sluice as 0.25 meters. So now we can we got the area, so therefore providing a circular opening, so we get the diameter as 0.2. However, we can provide 0.4 meters, 0.45 meters of a circular opening, which will be done in a RCC diaphragm wall, which will be kept at the entrance of the barrel. So generally the barrel, the minimum vent way for the sluice barrel is 60 centimeters by 75 centimeters high, 60 centimeters wide, and 75 meters height. So you can provide 60 centimeters thick concrete bed for the sluice barrel. So this is what this is the barrel, where the side wall is of trapezoidal shape, which is here, and this is the barrel, which is 60 centimeters by 75 centimeters height. We have provided 60 centimeters thick concrete bed. So you know that the sill of the barrel is kept at the canal bed level, which is 122.7. So keeping 75 centimeters and providing RCC slab 0.15 thick, so therefore we get this RL as 123.6. You know that the TBL is fixed at 130, which is again decided. So 130 minus 123.6 gives 6.4 meters of height of the fill. So this RCC slab has to support this its sulfide as well as the height of the fill. The various other quantities is assumed, like unit weight of concrete, which is 24 kilonewton per meter cube. Unit weight of soil is again is again taken as 20 kilonewton per meter cube. Angle of repose for soil is 30 degrees. So you can now this RC slab will be designed as simply supported slabs of clear span 60 centimeters. So therefore the effective span will be 60 centimeters plus 0.15 plus 0.15. So bearing is given as 30 centimeters. So therefore it is 0.15 plus 0.15, which comes to as a 0.9 meters. Now you know that the sulfide of the slab is 15 centimeters thick, so 0.15 into 24 comes to 3.6 kilonewton per meter square. Weight of the fill is 6.4 meters. The height of the fill multiplied by the unit weight is 128 kilonewton per meter square. So the total dead load that is coming on the RC slab is 131.6 kilonewton per meter square. Now you can calculate what should be the bending moment, which is WL square by 8. So you got this. So you for ultimate moment you can multiply by 1.5, so and get ultimate moment, which is 22.2. so now you can check the depth whether the RCC slab provided is safe or not. So 0.138 FCK BD square is equal to mu. So therefore because we have used M15 concrete, FCK is 15 Newton per mm square, B is 1000, mu you can take it 22.21 into 10 raised to 6, so we get the effective depth as 103.58 millimeters. So using 20 mm effective cover, you can have the overall depth as 123 millimeters, but we have provided 150 millimeters, so hence it is safe. So this is what this is what we have assumed. So all these things. Now we have to go for the stability of the side walls. So when you do the stability of the side walls. Okay, so now we have the stability of the roof. It is divided into various portions. So now this 6.4 meters is the height of the fill. So therefore we are dividing into suitable portions like here. So this is P1, which is the weight of the slab. As for the weight of the fill, we have calculated the dead load. So from the dead load, the span is 0.9 meters. WL by 2 will give the reaction. So that reaction, the slab as well as the weight of the fill is transferred as reactions, which is P1, which is WL by 2. And we also calculate the weight of the earth, that is P2. Similarly, weight of the earth, which is P3. So again the triangular portion is P4, and similarly we have the weight of the concrete here. This portion is P5, and similarly the triangular portion of the concrete is P6. So now we have to calculate what is the earth pressure. So earth pressure here is where intensity of earth pressure is Ka gamma into H. So what is H here from here to here, which is 6.4 meters. What is Ka? 1 minus sin phi by 1 plus sin phi, that is 1 minus sin 30 by 1 plus sin 30, which comes to 1/3. So 1/3 into 6.4 into 20 gives 42.67. Similarly 6.4 plus 0.9 at the bottom, so which will come to 7.3, that is 1/3 into 20 into 7.3 gives 48.67. You can divide into suitable portions, that is rectangular portion is P7 and triangular portion is P8. So what is the remaining ordinate for this? 48.67 minus 42.67 comes to 6 kilonewton per meter square. So therefore in order to calculate P7, it is the area of this diagram, which is 42.67 into 0.9 into 1 is P7. Half into 6 into 0.9 into 1 gives P8. So like this I will tell you one calculation, because later on I will not tell you. So for example P1, you know WL by 2, and what is P2? It is 6.4 into 0.45 into 1 into 20. What is P3? It is 6.4 into 0.55 into 1 into 20. So P3 is over. P4, half into 0.55 into height 0.9 into 20, like that. So then what is P5? It is concrete. So 0.45 into 0.9 into 1 multiply by 24, because it is concrete. Here half into 0.5 into 0.9 into 1 into 24, so multiplied by 24, so that gives P6. So like this we are able to calculate it. So now the moment is calculated about this point. Yeah, so each of the lever arms you should calculate. For example P1, because it is lying at this is the bearing is 30, so it is 0.15. Similarly for P5, this is 0.45, it is 0.45 by 2. What about P6? It is 0.45 plus one third of 0.55, like this. What is P2? For P2 lever arm is 0.45 by 2. What is lever arm for P3? It is 0.45 plus half of 0.55. Then what is the lever arm for P4? So that means till you can come down till here, which is 1 meter. So you can deduct this portion, 1 minus 0.55 by 3, or you can take 0.45 plus 2/3 of 0.55. So what is lever arm for P7? P7 is this, half of 0.9. What is lever arm for P8? It is one third of 0.9. So like this. So now you know that P1, P2, P3, P4, P5, P6 is making anti-clockwise moment about A. So they are entered in the resisting moment, whereas P7 and P8 are making clockwise moment. So therefore they are entered in the overturning moment. So this is the calculations part for the stability. So coming to the calculation part, so we have here, so each of the calculations have shown, I already explained. So so we have, so now each of the calculations are shown. For example, P1, P2, P3, as I explained earlier. So vertical forces are entered, which are all downward forces. Horizontal forces are entered here. So distance to to A is already calculated and entered here. So now force into distance gives the moment. So because these all forces will give, because this entire thing is the resistance, because anti-clockwise moment, so entered here. So these two is giving overturning moment, so this is entered here. So now you are, by taking the sum total of this will give sigma v. Similarly, sum total of these two will give sigma h. Then sum total of all this will give sigma mr, and similarly this will give sigma m naught. So now you can find out what is the net moment. Net moment about the sigma mr minus sigma m naught, which gives sigma m. Then sigma m by sigma v will give the distance of resultant from A, that is x bar. So the eccentricity is b by 2 minus x bar. So b is nothing but 1 meter that we have assumed. So 1 by 2 minus this, which will give 0.21. So b by 6 is 0.17. You know E is slightly greater than B by 6. However, we can calculate P max sigma V by B into 1 plus 6 E by B. Similarly, P minimum will be little bit tension, but for masonry it will be allowed up to 125 kN per meter square. However, for concrete it can be go up to 250 kN per meter square. So that means whatever the side walls that we have assumed can be always taken and provided as and then you can assume that that sections of the side walls, because, and even the factor of safety is coming very much higher, which is factor of safety against overturning you can calculate by sigma mr by sigma m naught, and similarly factor of safety against sliding you can calculate as mu sigma b by sigma h. So both are safe. You also know that we also have a tower head. The tower head will be provided somewhere near the entrance of the barrel on the upstream side, where the top of the tower head should be at least 0.3 meters above the maximum water level. You know that the maximum water level was fixed somewhere at 128.5 in our design sheets. So we give 0.3 meters freeboard, which comes to top of the tower head is about 128.8 meters. So now the tower head generally is of a concrete or a masonry wall, so where the internal diameter of the masonry wall or a concrete wall is 1.25 meters diameters. At the top section, at the top, the thickness of the wall can be kept as 0.45 meters. As we move downwards, the pressure of water increases, therefore you can increase it to about zero point 0.6 or 0.65 meters. So this is the section of the tower which is shown. And then we have, so if it is very near to the bund, the so here the top of the bund is very near, a person can the steps can be provided here, and he can come here and then he can regulate the gates. Otherwise, if it is very far off, a little bit far off, then you can extend this to the top and provide a footbridge somewhere here like this. So a footbridge can be provided and this can be extended up to the top. A person can come here and try to regulate. So this wall has to be extended right up to the top of the bund. But if it is very nearer to the bund, steps can be provided. However, a person operating man can come here and then he can regulate the wall. So this is the drawing part which is pertaining to whatever the design sheet. I told you that this is the regulating arrangement. A person can come over here and then go here and simply regulate, and this is the diaphragm wall that you have provided. So there is a 45 centimeters opening, and then the shutter gates are provided, so which is regulated here. So a person can come here, simply lift it, and then the water enters here. So that means there is I told you that the sill of the barrel is kept at 122.7, whereas the top of the RC slab is 123.6. We know the TBL is 130. We are given slope 2 is to 1. So we have fixed the top of the tower head at 128.8. So now you know that this is the top here after water flowing. So it has to go to the cistern. So now a cistern has to be provided. Generally, the width of the cistern is 2.5 meters. The length will be decided according in the as in the drawing. So this length automatically gets fixed based on. So now we have provided canal width as 0.5 meters. We are given slope of the canal as 1.5 is to 1. So therefore here the canal bed is at 122.7. So 122.7. So here the water depth that we have fixed is 0.5 meters. I have given another 1.5 meters is the freeboard. So 1 meter is the difference. So 122.7 plus uh, so this is 0.75 is the I think depth of the water. So zero point 0.5 plus 0.75 plus zero point 0.5, I've given somewhere around 1.25 into 1.5. So that comes to about this TBL RL is up to 124.2. So therefore you can, and then the ground level is fixed at 123.2. So we have to see the ground level at the site, which is 123.2. So this is how you, this is the plan at the bottom, plan at the top, whereas long section is been drawn according to the RLs that we already learned in the in our irrigation design class. So it should be easy, and I have already explained you about this, how to draw this tank sluice part, and so that it will be very easy for you to reproduce whatever the designs that you have done for particularly for extensive survey project, and the same data has been transferred to the drawing sheet. So that will be the advantage for you for learning hydraulic structures design and drawing, which have been taught already in a separate course for you, and so that you can so same drawings is made use of here. That knowledge has been made use of here to use it for extensive survey projects. So coming to this, now we have to also have to provide a surplus weir. So why a surplus weir is to be provided? A surplus weir is to be provided to see that you have the excess water has to be sent to the downstream side, particularly during the flood. So we already decided the catchment area. The catchment area is, it is 2145 triple zero meters square, which comes to about 2.15 square kilometers. You have Reeves coefficient, so this is Reeves coefficient, so which is taken as that is around 10. So therefore we can find out what is the flood discharge. So flood discharge is 16.66 meter cube per second. So you know that the crust level of the weir is kept at the full tank level. We already decided the full tank level, which is at 128. So maximum water level also we have decided, which is 128.5. So therefore the driving head for the weir is 0.5 meters. You know that Q is equal to 2 by 3 CD root 2 GLH to the power of 3 by 2. So you know the flood discharge, you know CD 0.6. So we can find out what should be the length of the weir. So, and the driving head is 0.5 meters. So the length of weir comes to about 226.6 meters according for the dam stones. So we can fix the length of the weir as 30 meters. Now the cross section of the surplus weir has to be decided. The top of the weir is kept at the top of the weir is kept at FTL, that is, so that RL is already fixed, which is 128. Maximum water level is 128.5. So therefore the head over the weir is 0.5 meters. So hard soil foundation at the site is already decided, which is 125.5. So you can keep the foundation level somewhere 50 centimeters below the hard soil, so that fixes the bottom of the concrete bed. So therefore you can have 60 centimeters thick concrete bed. So therefore the top of the concrete bed is fixed at 125.6. So now you can decide the height of the weir. So height of weir is, So the it is the top of the weir is at FTL, which is 128. So 128 minus 125.6 gives height of the weir as 2.4. So now you can use some thumb rule to decide what should be the top width of the weir. So it is given by 0.55 into root of the height of the weir plus the root of the head over the weir, so which comes to about 1.24 meters, which is say 1.3 meters. So provide bottom width of the weir equal to height of the weir, and also provide equal batters on both sides of the weir. So now the bottom width of the weir can be fixed as 4 meters. So this is the section of the weir, so which is top width is 1.3, bottom width is 2.4, height is also 2.4 meters. So we get a driving head of 0.5 meters, which is this level is maximum water level. So now we know that. So you can already draw the water pressure diagram. Now here this when there are dam stones and the water will be filled up to the maximum water level, so we get a water pressure something like this. So that means this is nothing but gamma into, that is specific weight, into H 9.81 into 2.9 gives to 28.449. So you can do the stability analysis for the weir. So now the what is the weight of this weir? So it is 1.3 plus 2.4 by 2 multiplied by the height is 2.4 into 24 is the unit weight of concrete, which comes to 106.56. We take a distance to A, which is 1.2, so therefore we get a resisting moment. So similarly W2 can be calculated, which is the weight of this water here. So it is 0.5 into this distance, which is 1.2 into 9.81 gives vertical force. So therefore the distance of W2 to A is 1.8 meters. Similarly you can calculate resisting moment. So W3 is the weight of the water in the triangular portion, which is 0.5 into 0.6 into 1 into 9.81. So the distance to A is 2.2, so that gives resting moment. Similarly the water pressure can be calculated half base into height, so which gives as of 41.25. So where the distance is 2.9 by 3. So therefore we can take summation of vertical forces, summation of horizontal forces, summation of resisting moment, summation of overturning. Similarly, the net moment can be calculated by sigma mr minus sigma m naught, so that gives 104.93 kilonewtons. So distance of resultant to A is that is sigma m by sigma v, which comes to 0.91. Eccentricity can be calculated as b by 2 minus x bar, which is 0.29 meters. So similarly b by 6, because we have taken 2.4 meters as the base width, 2.4 divided by 6 comes to 0.4. Hence E is less than b by 6. Therefore we can find that P max and P minimum are both positive quantity, so therefore there will be no tension anywhere in the base of the weir. So therefore the assumed section of that is 1.3 at the top and the bottom 2.4 can be provided. We also calculate factor safety against overturning, which comes to 3 sigma mr by sigma m naught is 3.62, which is greater than 1.5. Factor safety against sliding is mu times sigma v by sigma h, which is again greater than 1, hence the downstream step apron. So the aprons are provided on the downstream side in a stepped fashion. So therefore there are two aprons that are provided. The first apron will be kept at the general ground level. Therefore the general ground level here below the surplus weir is about 126. So therefore no, at 127. So the first apron will be kept at 127, and next the second apron will be kept at the level 126. So now we have the maximum water level on the upstream side as the MWL, which is 128 point. There is no flow on the downstream side. So therefore we have since there is no flow on the downstream side, so we have 128.5 as the water level on the upstream side, whereas 126 on the downstream side. So 128.5 minus 126 will 2.5 meters of the seepage head. So taking Bligh's creep coefficient as 5, so C times Hs will give the total creep length, which comes to 12.5. So now the water will percolate below the weir, that is into the soil, and then comes out at the end of the apron. So that length is AB plus BC plus CD plus DA. So now you know the length AB. Okay, you know the length BC, you know length DE. So that comes as 6 plus CD. So this 6 plus CD should be equal to 12.5. So that means CD can be calculated as 6.5. So that means you can assume it as 7 meters. So two aprons, that is I told you is a stepped aprons. The first apron will be for 3 meters, which is 1 meter thick, and 4 meters the length of the second apron, so which is of 0.5 meters thickness. So this is the sketch of the aprons that we are providing. So the first apron will be kept at the level 127, which is general ground level. The second apron will be kept at level 126, which will be below the ground level, below the surplus weir. So we have the thickness of the first apron as 1 meter, thickness of the second apron as 0.5 meters. I told you that the maximum seepage head is 128.5 minus 126, which is 2.5. Now the water creeps like this, water seeps like this and comes out. So what is the meaning of this? So by the time the water comes, there's always resistance to the flow, so head goes on reducing, and by the time it comes here, so the head has to be 0. So that is what it means. Otherwise, if there is enough seepage head, then it tries to remove the soil, and so that soil will removal of the soil continues backwards, and then may come at the upstream end. So therefore a tunnel like formation may take place, which is known as a piping here. So that's why, to avoid that, we have to see that there should be enough length of the aprons. So now here the creep length from A to F, A to E is, that is AB plus BC plus CD plus DA, which should be equal to C times HS, which is 12.5. Therefore we got CD as 7 meters. That's why we have kept this as 3 meters and 4 meters. Now we have to decide whether this thickness of the apron is sufficient or not. So now we have to find creep length from A to F. So what is creep length? It is AB plus BC plus CF, which is given here. So which AB is nothing but 127 minus 125, which comes to 2 meters. So this is 2.4 plus 0.3 plus 0.3, which comes to 3 meters. So BC is 3 meters, and this is since thickness is assumed as 1 meter, so it is 126 minus 125 as 1 meter. So therefore 6 meters is the creep length. So what is the head lost? So it is divided by C, so therefore 1.2. So by the time it comes over here, the head lost is 1.2 meters. What is the remaining head or residual head? So out of 2.5 meters, 1.2 gone, so therefore it is 1.3 meters. Now we know that the uplift pressure will be 9.81 into 1.3 should be equal to 24 into thickness. So therefore the thickness of the floor is to be provided such that the weight of the floor has to balance uplift pressure. So now allow any others extra 33% thickness to withstand any variations. So therefore you can multiply by 4 by 3, that gives about 0.7 meters. So therefore I have provided 1 meter. So this is what you do for the second apron also. So you find the creep length, that is AB plus BC plus CG. So CG you can approximately take as 3 meters. So therefore you will get the total creep length. So divide by 5, you will get the residual head. You will get the head lost in percolation. From 2.5 you deduct head lost in percolation, you will get the residual head. So uplift pressure has to be equal to weight of the floor. So that will decide the thickness here. Is what is done here. Creep length from A to G is given, which is 8.5. So 1/5 of 8.5 gives 1.7. Out of 2.5, 1.7 goes as head loss. So therefore you will get residual as 0.8. So now you know that uplift pressure 9.81 into 0.8 should be equal to 24 times the thickness. So thickness comes to just 0.33. You can increase by 33%, so that you will get 0.44. So we have provided 0.5 meters as the thickness. So this is how you decide the length of the aprons as well as the thickness that has to be provided for the stepped aprons. So this is the sections, that is the plan that we have shown. So where the weir consists of an abutment, wing walls, and the returns. So this is the bund. The slope of the bund is 2:1, 2:1. We already done in the we have fixed the TBL, which is 130. Now how to fix the sections? So this is the upstream side, this is the downstream side. We know that always any wall, the top of the, that is we call it as a return wall, so you should not go below the ground level. We know that the ground level is at 127, so therefore the top of the return is kept at 127. So now the wing wall is sloped from 130 to 127. Generally this downstream wing wall is given a supply of 1:5. So now when you come over the upstream side, the water level goes to about 128.5. So that is the maximum water level. So give a freeboard of 120 128.5 to that is about 0.3 meters to maximum water level, so that comes to 128. So any wall has to be kept at 128.8. So now therefore the wing wall is sloped from 130 here and goes down to 128.8. So by the time it comes to section 3, so it has already reached 128.8. So therefore as you go with a slope of 2 is to 1, it will go below 128.8. So that's the reason from section 3 you have to go on keeping the top as 128.8. So now you have to decide for each of the sections here. So now for every year the see the bottom width should be decided. So bottom width is given by simple thumb rule, like it is always zero point 0.4 times the height. So you know that the bottom of the abutment is kept at 125.6, which we have already decided. Water side battery is always kept as 1:8. So the height of the abutment is 130 minus 1, because the top of the abutment is kept at 130, bottom is kept at 125.6. So therefore bottom width is zero point 0.4 times h, which comes to 2 meters. So similarly, I told you downstream wing wall is always the top of the downstream return wall is kept at general ground level, which is 127. So therefore downstream wing wall is sloped from 130 to 127. So the same foundation which you provided for the abutment can be extended to the downstream wing wall and the downstream returns. So that's how decided the top of the return wall is kept at 127, bottom of the downstream return wall is kept at 125.6. So therefore the height is 1.4. So that thumb rule is zero point 0.4 times h for the bottom width. So you can go for at least 0.8 meters as the thickness, bottom thickness for the return walls. Similarly for the upstream wing wall, I told you that maximum water level is 128.5. You cannot keep it at the general ground level, it is well below maximum water level. So if therefore any height has to be above 128.5. So therefore we give a 30 centimeters freeboard to 128.5 and fix up the top of the return. So therefore when the wing wall is sloping from 130 to 128.8, so some portion of the wing wall will go below 128. So therefore after section 3 we have to keep level at 128.8. So now the bottom of the downstream return wall is kept at 128, so whereas the bottom is kept at 125.6. So therefore that gives the height. So therefore zero point 0.4 times h will give 1.4 meters. So downstream wing wall is given a sply of 1:5, whereas upstream wing wall is given a sply of 1:2. So these are the sections that you have already provided. So that is 130. So this section 1. So 2 meters is the bottom thickness, bottom width. Similarly for section 2, bottom width is 0.8 meters. Similarly for section 3, it is 1.4 meters. So same sections. Water side battery is 1:8. The earth side batteries is automatically fixed after you draw this. Now this is the drawing that we have already taken. So you should be able to draw rounded sections, half round sections, half round elevations. Similarly, you have to draw half plan at bottom, half plan at top, and also you have to draw the section across the weir. All the levels are decided. That is based on the designs that we have done. So these drawings have already been taught in the hydraulic structures design and drawing. So you can reproduce the drawings and fix up the levels that you already decided in the extensive projects. So this is the complete tank project that you have to do. And whatever that you have done the survey on the site has to be reproduced onto the drawing sheet, so that these drawings can be done. And also we expect you to do before doing the drawings, it is not simply draw. You have to draw, you have to design all the components that you are required to do. I didn't concentrate much about the earthwork calculations which you will be doing. It is a part of the survey work. After you do the survey work, you already have fixed the top of the bund. Now for using the top of the bund, you already have the L sections and the cross sections that you have to, all the levels are already done. So now you can fix up the top of the bund onto the sections there and decide the earthwork calculations. So that is the part of that survey work, and you can do the volume of the earthwork that has to be done for the bund. Also you can calculate what should be the earthwork calculations for the canals, like this. So you can finish off this tank project. Hope this particular video lecture was very helpful for you, and you can go through all my designs that I have done and decide decide accordingly. Hope you will make use of this lecture and do accordingly whatever the steps that I have shown. Thank you very much.